All right, so now we're going to look at convergence for alternating series. In the last videos, we were looking at convergence when it was a sequence of all non-negative um, non-negative terms. But now we're looking at alternating series. Alternating is when you're going to have values going minus, plus, minus, plus, minus, plus, as we can see right here. Minus, plus, minus, plus. And the way we create that is from that minus 1 to the n, or minus 1 to the n plus 1. Um, and what we want to look at is how we want to create a framework for how we can decide whether or not these series are converging or diverging. And there is an appropriate test here. It's called the alternating series test, and it's two checkpoints for us to see whether or not a series converges if it is in fact alternating. So the way that we test this, two conditions need to be satisfied. The first one is that the the last term, or the nth term, as n approaches infinity, our nth term must approach 0. So in other words, we're adding negligible amount in our last term. So the first thing that we need to check for is, does the last term approach 0? Not the series approaching 0, but does the nth term approach 0? And then the last thing, or the second piece, the second condition that needs to be satisfied is that a sub n is decreasing, meaning it's getting smaller in value. So the n plus 1th term is less than the nth term. And, and I think what we're talking about is the absolute value of. Um, so, if we look at the top, the top case, we've got, 1/2 and 1/3. Uh, 1/2 is bigger than 1/3, so that satisfies this. Or to put it more in this language, um, our a to the 2 plus 1 term is less than our a to the 2 term. That's going on right there. And for every single case, the a to the n plus 1 term, the absolute value of, is less than our a to the nth term. So we're decreasing. Each term is decreasing. What does that mean? Well, if you think about it, we start off looking at this case. We start off with 1. Then you subtract a half, but you add a third back. So you take away a bunch, and then you add a little bit less back. And then you take away a bunch, and then you put a little bit less back. Um, and eventually, we're not really adding much at all. We're not adding anything at all. Okay, so let's look at that. We've got this. What we were just looking at, is it convergent or divergent? So the first thing we need to say is, the first condition, does the limit as n approach infinity of a sub n, does it equal 0? So we're saying the limit as n approaches infinity of -1 to the n plus 1. Well, that's just going to change sign, minus, positive, and then we have 1 over n. So really, we can essentially just ignore this alternating term, or alternating factor, and we're really just looking at that. And as n approaches infinity, this equals 0. And it's approaching 0 from both sides, like positive and negative and positive and negative, but each of those terms is getting close to 0. Next, is it a decreasing so that met the first condition. And then the second condition, is it in decreasing? Is it a decreasing sequence? Yes. You know, 1/2 is less than 1, and 1/3 is less than 1/2, and 1/4 is less than 1/3. So each subsequent term is less than the one before it. So therefore, that implies that this alternating harmonic series, in fact, converges. Next, what we want to look at is, so if something in fact does converge, we want to think about an error estimate for an alternating series. We want to think about, well, if, for example, if we use some value for n, like if we use only 5 terms or 10 terms or 12 terms, what is our error going to be? And the error analysis for an alternating series is that sum, the actual sum when we let n approach infinity, um, minus the sum that we calculate for some value n. The difference between those, the difference between the sum uh, and our calculated sum. So in other words, this is the actual sum, and this is the sum approximation for n equals n, some number. That this difference, the absolute value of this difference, is going to be less than our n plus 1th term. And we're not going to go through a too much of a formal proof of this, but what this is saying is that the difference between the actual sum and our approximated sum is going to be less, the absolute value of that is going to be less than, so this is our error. Our error is going to be less than the n plus 1th term. How do we use that? Well, let's look at an example of that. So we've got this alternating harmonic series that we've looked at, and it says estimate the sum of the series by taking the sum of the first 4 terms. So we want to estimate s. We want to estimate s, and we're going to estimate s by finding s sub 4. So we need to find the first 4 terms. Well, s sub 4 is 1 minus 1/2 plus 1/3 minus 1/4. And if we get those all to 12ths so that we can add them, we see that this is 12 minus 6, which is 6, plus 4, 10 minus 3. This equals 7/12. So S sub 4, so using 4 terms, my approximation for my estimate for S is 7/12. Well, how accurate is this estimate? How accurate am I? Well, I know using this error estimate for alternating series, uh, I know that the actual sum minus my approximation is going to be less than a sub, well, 4 plus 1, because I was looking at 4 terms. So then we need to find a sub 5. Well, a sub 5, using my value for a sub n, which is negative 1 to the n plus 1 times 1 over n. Well, so a sub 5 would be negative 1 to the 5 plus 1 times 1 over n. Well, 1 over 5, rather. And this equals 1/5. So our 5th term is 1/5, and that this value is as big as our error estimate could be. Said more succinctly, we know that the actual sum minus s sub 4, which we found as 7/12, must be less than 1/5. So if we want to, actually get a range for this value, we know the following. We know that s must then be solving this absolute inequality, s must be less than 7/12 plus 1/5 and greater than 7/12 minus 1/5. And I'm not going to go through finding out what those fractions are. We can just leave it like that. But what that allows us to do is, if we don't want to go through evaluating, letting n approach infinity, we can just use, 4 or 5 or 6 let n be 4 or 5 or 6 and use that as an approximation for what is my um, what is my value of s. So now I have a range of values of s. So I've honed in on what s might be, and I've done that simply by only finding s sub 4 and a sub 5. Okay, and then the next question um, says how many terms of this series, and maybe I'll put this on another page so that it's a little bit more clear. So it says how many terms of this series would we need to take in order to get a partial sum s sub n within 0.005 two decimal places of the sum s. So how many terms of this series would we need to take? So in other words, find n. How many terms of the series would we need to take in order to get a partial sum s sub n within this many decimal places of the sum? So what we're saying is s minus s sub n must be less than 0.005. Well, I just had a weird computer thing that the recording button didn't catch. So let me just go back and make sure um, that we're clear on what's going on. For this, it says how many terms of the series would we need to take in order to get a partial sum, S sub n, within 0.005 two decimal places of the sum. Um, so we want we want our approximation, S sub n, to be within 0.005 right here. So what we write is s minus s sub n. That's going to be our error. Our error, s minus s sub n, must be less than 0.005. That's the restraints that we're putting on. Well, you know, our error 0.005. This is um, typically a sub n plus one. So what we could think about this the other way is that a sub n plus one must be less than or equal to our error 0.005 if our approximation is going to be as good as we want it to be. Um, with our restrictions. Well, a sub n plus 1, ignoring the alternation of positive negative, a sub n plus 1 is just 1 over n plus 1, and that needs to be less than or equal to 0.005. So really, we just need to solve this inequality for n, and it's a a rational inequality. So we get n plus 1 must be greater than or equal to 1 over 0.005. We can simplify that to 200. This is 200. Must be less than or equal to n plus 1. Subtracting 1, we get n must be greater than or equal to 199. So as long as we, if we find s sub 199, as long as we find s sub 199, that's going to be within 0.005 of the actual true sum. So if we let n be 199, we will be within this small error range that we've required, this error range of our approximation for the actual value s. Okay, well, we've talked about the convergence of a harmonic series, and what we've been talking about is does that alternating harmonic or does that alternating series, does it converge to a value? Well, we want to extend this idea to talk about absolute versus conditional convergence. And I think what would be fitting is I'm going to stop this video right now, and we'll look at that video in the next um, we'll look at that in the next video. So we'll continue on in just one more video, but I'm going to pause it now.